Houston and Wichita Falls and Dallas.
Okay. So it's a big state, so they've got 6 sort of regional offices, if I counted right, in addition to office in Austin. You ever get confused with Jeff Payne? Have you met Jeff? He works for BEG in Austin.
Yeah, I've met him a few times.
Scott is in charge of all the management of these ranches and the grass you see, and you know, keeping the place looking like it does and producing. And so Dr. Scott's going to chat with you a little later. But if y'all have any questions for these guys, don't hesitate to ask them. They're out here.
So your control keys are in these areas. You can cycle these top menus. Well, this is the memory screen. So there I'm on memory. You can go to the tools for the different settings. So to start with, we want to go to configuration, select mode, just hit enter. And I've got it set on the 24 electrode 2 meter spacing with the dipole array first. And I'll explain later what the dipole array is. You can give it a file name. You can give it, yeah, but I mean in here you don't really need to do that. You can do that all in the post-processing on the computer. It's a whole lot easier than trying to type it in. Escape that of there. Hit it a couple of times. Stack menu, you can tell it for each measurement you want to take 5 repeat measurements and or 10 repeat or however long you want to take to make sure that your error between measurements is minimized. So we usually do 6 measurements on each one, and then on to the next setting, as long as they're all within a 3% error. And then transmit on or receive on. We always just use a simple square array. You know what circumstance you would ever run across where you would want to use the maximum voltage to transmit us. Let me go grab another one. Fast and try it.
Well, downstream
of the dam, there's some. But this is the headwater. This is where the North Concho and Middle Concho meet, is O.C. Fisher. And then what we were looking at is the Middle Concho comes out of this lake and it goes down to the town. You remember that first day when we went to the convergence? This is kind of up above all of that town, and the town runs right over there.
Spring Creek is in the middle or the center?
To the middle.
That's upstream of this location.
And so it's had a 1% or less capacity. This is famous. Do y'all remember or ever heard of a guy named Johnny Carson?
He was a talk show host in the United States on television for years, on late night television.
And in the 80s, this reservoir dried up like this, and it caught on fire. And they did this big national make fun of this whole thing because our reservoir was on fire. It's the only lake in the world on fire, I guess. Sea fishing. All structures are where this beetle got away from that particular tree, and it went into an indigenous tree and killed them. And these were huge trees, like the size of this pickup bed in diameter. So, and this kind of vegetation you don't want to see around water. You can see it up there too, kind of everywhere. And so that's causing us to lose a lot of water to the air that we normally wouldn't lose. This is a huge area of research. I bet we
so that you can correct everything in time back to what the response should have been at that one site. So each one of these files will have two, we just call them base stations, but you can see I scroll through each of the, on the PDA, every time you hit the log or whatever, you start a new line. So here, this would be one line. That would be line 2, 3, 4, 5, and 6, back to the base station. And this is a program we actually wrote in-house, so it's not super fancy by any means. So at each one of these base stations, to begin with, we would come in and just remove anything that doesn't look nice and steady, because the ideal is you put it down like this in the early times here. It could be when the instrument was still heating up a little. You want it to be a nice steady response at your base station. So here we would just remove everything from there back. In both the in-phase the actual data collection lines, where I was talking about on the PDA, you can hit mark if you walk over a metal plate or something. That's what these bright red lines are. That's just the marker in the file that reads in as a red line there. So instantly we can throw out any spikes around that that's within 10 meters before or after. Let's see if that looks. Oh, let's just go ahead and get rid of those. Now, if we come back to that, it should rescale everything to take those huge spikes out. So it's looking a whole lot better already there. We can go through and look at the others, just remove anything blatantly obvious. So that's got all of our pre-marked stuff taken out of the file. And then we've got filters in here for despiking. You can set the number of points and the factor of spikes you want to remove to get rid of these huge spikes that weren't marked in the file, but I mean, just common sense says that's not a real phenomenon. So, and we got the option, you could do it by box, the current line, or just despike the whole data set. For now, I'll just despike the whole data set. So we could go through and change those spikes.
Factors.
Say it again.
Just say the factors. We can change these factors.
Yeah, you can change the factors and despike it more, but there's no need to play with it that in depth right now, just to get the idea of how it works. The over here, the profile smoothing, that's the inversion program wants all the data points to be lined up on top of each other for each sounding, and right now it kind of collects like our 15 frequencies. It steps through each one every 1/10 of a second or whatever, so they're all spatially located slightly different. So we need to smooth across that like 2 meter space and put it in one column spatially, if that makes any sense. So we'll just say 3, and we'll just go ahead and smooth the whole data set. And here you can smooth across 10 points, depending on how smooth you want to make
And
it.
this is mean, the method of the statistic method of smoothing. There is mean.
Yeah, and you got a few options we wrote in there. I think mean, median, average.
Average, yeah.
It's, okay, so once all that's, where's it at? Drift correct. Okay, over here, we've got the final processing. You can drift correct for your base stations. So if at this base station we knew, like say we had a DC line or a well 10 foot away from it, like we knew what the electrical conductivity should be down that at that sounding, we can zero all this data out using that base station. Just call this 0 and everything else relative to 0, and then add back in the in-phase and quadrature response that would be expected from the known conductivity of that base station. Right now we don't have the, I mean, I don't know what the in-phase and quadrature should have been, so right now we can just drift correct. And here, let me do one thing first. This will help. Program rewrote's not quite advanced enough for Windows 7, so it looks a lot better in the older screens. Where's that? Oh. There we go. So now process that. Of course, we could have went in and filtered these a lot more, but now everything's shifted in time to those base stations because everything has a timestamp. Does that make sense? So any change between those two occupations of that base station, that change has been spread over time to all the data points. So now we should have And that was a really quick run through of the pre-processing program. Now we've got these output data files that the program wrote. You can open that up. And it's just your in-phase quadrature response for each of your frequencies, and locational data, power line noise, stuff like that. So the next step would be the inversion program, which is WinGem that comes with it, the Gem tube. I mean, that's there. It comes with the system. So there are others available, but this works as good as any. So we just use the inversion module. Seconds. That actually looks right. What's not working? So it's just because it was open. Okay, so the Gem 2 orientation, we almost always use it horizontal coplanar. Apparently you can hold it upright and collect data. I'm not sure what that would gain you. The coil separation's always 1.66. Sensor height, I mean, normally we would measure it depending on the user, how far away from the ground it is. But for this purpose, we'll just say it's 1 meter. You can give it a number of layers you want to put in your starting model, usually between 2 and 6 or whatever. For right now, we can just go with the defaults. You always want to start each sounding independent. I mean, you can start it based on what the sounding before that had, but we've noticed that causes some problems on the back end. So. And then include the EM data. So now here's the actual inversion running. I don't even know why they show you anything, because none of this means anything to anybody. You can see down here the fit error is terrible right now, so our starting model is nowhere close to what it should be. I mean, we could run 30 different inversions on this data set and get that error down to about 10% usually. Normally we would put this into the whole file into a geodatabase somehow and sparse out 1 point every 10 meters or something, and then run inversion that to figure out what the starting model and everything needs to be, because this is a short data set. It's only 8% done now. But if we put this whole study site into there, it would take it the weekend to run all the inversions. So you speed it up any chance you get. I'll just kill that for now. But
This is the data of this morning.
No, this is from that Sandy Beach site. The data we collected this morning, we didn't have the GPS hooked up, so I mean, we could look at it, but it's not going to show anything. There wouldn't be any spatially, it wouldn't mean anything. So.
Any sense? Does it make any sense?
It doesn't make any sense?
The data, our data.
Yeah.
Yes, I see.
Okay. So, real quick. Where's it at? Well, I'll show you the final figures here.
Was it based on pathology?
Yeah, we're imaging the gravel bed that's carrying the contaminant. So from 11, let's just start out with looking at some of these. So in 3D space, once we've inverted all those lines, plotted them in 2D, and then create 3D voxel models off of that 2D data. You can plot it in 3D, and in the actual database, you can rotate this up and change the scales and everything. This is just a still picture because I didn't have that much space on the memory card. But we can look at this, you see the red down in here? It's kind of hard to see, but that's the resistive feature from the frequency domain EM. The green stuff is from a totally different technique that we use at the same site, but it has to be used on like roads that you can drive down. You can't drag it through the trees kind of thing. 50 sections. So just showing 2D, I mean this is kind of hard to see, but